Hello, today we're going to look at electronegativity, and it's presented to you by Science Visualized. This is part of Organic Chemistry 1. Covalent bonds. They are bonds that are formed by electron sharing. That's the most important part, electron sharing. Polar covalent bond. These are bonds that are formed by electron sharing, where the shared electrons are attracted more closely towards the more electronegative element. So that means the electrons are unequally shared. For example, if you're forming a bond between X and Y, and the electrons are closer to Y, then we say Y is more electronegative. That means the shared electrons will be pulled closer to Y, and therefore Y will have a partial negative charge, so we use delta minus, and X will have a partial positive charge, we use delta plus for X. You can also use this arrow where the head points to the partial negative and the tail with it almost looks like a plus sign, points to the partial positive. So that's called a dipole. So what's electronegativity? It is the ability of an atom to attract shared electrons towards itself. Electronegativity increases across the periodic table from left to right. So it increases from left to right and from bottom to up. So it increases up the group in the periodic table. Symmetrical covalent bond. These are bonds where the electrons are equally shared. So if the two atoms are close in electronegativity, then the electrons will be equally shared. Or if the two atoms are equivalent, so for example, hydrogen, oxygen, you have the electrons equally shared between the atoms. So in this case, we're using X and X. That would be a symmetrical covalent bond. Ionic bond. These are bonds that are formed by electrostatic attraction between positively and negatively charged species or ions. So for example, sodium chloride, where sodium is positively charged, we call that cation, while the chloride is negatively charged, we call that anion. So the key there is electrostatic attraction. Also, some books will say electron transfer. So sodium loses an electron to form a positive charge, while chlorine accepts an electron to form a chloride ion, which is negatively charged. Inductive effect. This refers to shifting of electron density through single bonds. So sigma bond, single bond. So that's sigma bond. So when electron density shifts through a single bond, we call that inductive effect. Resonance effect, on the other hand, involves shifting of electron density through a pi bond. Pi bond. And remember, pi bonds are found in double bonds and triple bonds. A double bond has one pi bond and one sigma bond. A triple bond, on the other hand, has one sigma bond and two pi bonds. Dipoles, or a dipole, and we use this arrow with the head pointed to the more electronegative species and the tail, you cross it to look like a plus, pointed to the less electronegative species. So that's a partial plus, and this will be a partial minus, delta plus, delta minus. A dipole arrow is used to show polar bond. An arrowhead faces the partial negative. So you see the head here is facing the partial negative, while the tail facing the partial positive, delta plus. Dipole moment. Now, you should not confuse these two. A dipole is just an arrow pointing, showing the polarity of the bond. A dipole moment, on the other hand, is a result of addition of various dipoles in a compound. So in other words, you take all the dipoles present in a molecule and you add them up. If the net dipole is 0, then we say the molecule is not polar. If the net dipole is not 0, then we say you have a dipole moment which is not 0, and therefore we say the molecule is polar. So you have to consider the 3D shape, the 3 dimension of that molecule. So just a quick example. If you have a situation here where you have one dipole pulling to the left and another dipole pulling to the right, and all of them are equal magnitude, say with a force of 5 and a force of 5 pulling in opposite direction, what happens is that the resultant dipole moment is 0, and therefore we say the molecule is nonpolar. If on the other hand you have a stronger dipole pulling to the left, say with a force of 10, and a weaker one pulling to the right with a force of say 4, now the net dipole is going to be 10 minus 4, which will be 6 in that direction. So that would be the net dipole moment. So we say we have a net dipole moment, and this is a wrong way to, so we use an arrow for dipole moment, mu, and therefore we say the molecule is polar because it has a net dipole moment that's not equals to 0. These two examples are very easy because they're linear. It's very easy to add forces in a linear way. What if you're dealing with actual molecules where most of the time they're not linear? So for example, if you look at methane, you have CH4. The electronegativity difference between carbon and hydrogen is very small, and therefore we don't really say that carbon-hydrogen bond has dipole. So because of that, we say this is a non-polar molecule, because the electronegativity difference between carbon and hydrogen is minimal. So actually the rule is if the difference in electronegativity is less than or equals to 0.4, then we say it's a non-polar, so that's not a polar covalent bond. The whole molecule will be non-polar. Now, in case number 4, you have carbon tetrachloride, so carbon with 4 chlorines. Chlorine is further to the right than carbon, so therefore the chlorine will be partial negative, while the carbon will be partial plus, partial delta plus. So because of that, we draw the dipole arrow facing chlorine, and then you do that for all the other bonds, carbon chloride bonds. You have 4 of them. What you end up with is you end up with forces. So look at this. So that carbon is sp3 hybridized. That means you have carbon, and then you have one chlorine going into the plane, the other chlorine coming out of the plane, and then you have the remaining chlorine on the same plane with carbon. So that's how you represent an sp3 in 3 dimensions. So that means one dipole is pulling into the plane, the other one is pulling out of the plane. The net dipole of those two will go down like that. The net dipole moment, mu, will go down. And then on the other hand, you have this other chlorine dipole pulling away that way and this way. So the net dipole for that too will be in the opposite direction like that, but equal magnitude to this other one. So that means the final dipole is going to be the addition of those two dipole moments, which equals to 0. And because they cancel out, we say carbon tetrachloride, so CCl4, is non-polar because the net dipole moment is 0. Here's another example where we're using CH2Cl2. Again, we have to draw it in 3 dimensions where this carbon is sp3 hybridized. That means one hydrogen is coming out, the other one is going into the plane, and then you have the 2 chlorines on the same plane with carbon. We already said that the carbon-hydrogen bond is not polar, so it's not a polar covalent bond because the electronegativity difference between carbon and hydrogen is minimal. Now we are only left with carbon-chlorine bond, and you know that chlorine is further to the right, so it's partial negative, while carbon will be partial plus, and then same thing here, and you end up with these 2 dipoles pulling, one pulls to the left, another one pulls to the right, and the resulting dipole moment, so mu, will be equal to in that direction. So you end up adding or resolving those forces. And because the net dipole moment is not 0, we say that molecule, CH2Cl2, is polar. Now remember, if you drew this structure wrongly, you'll have carbon, chlorine, chlorine, hydrogen, hydrogen. This will be planar or flat, which is not the actual structure because it's not sp3. sp3 is tetrahedral shape and geometry, not planar. If you used planar, then you'll say that that chlorine dipole will cancel the other one, and therefore mu equals to 0, which is actually wrong. So that's wrong. The molecule is polar. Last example, we have water here, H2O. Oxygen is the central atom, and therefore you're going to draw two hydrogens on the same plane with oxygen, and then water has two lone pair of electrons. You're going to show one going into the plane and the other one coming out of the plane. Let me use a different color for the electrons, like that. So it's actually like oxygen is bonded to four things. We have one hydrogen, the other one, and then the lone pair of electrons. Each pair counts as an atom. So because of that, we say that oxygen is sp3 hybridized, and therefore the geometry is tetrahedral. The shape is not tetrahedral because for the shape you only consider what you're able to see. You see the hydrogen, oxygen like that, and because of that, you say water is V-shaped or bent. So the geometry is tetrahedral because it's sp3, but the shape is V-shaped or bent. Now the hydrogen-oxygen bond is polar, where oxygen will be partial negative, so you end up drawing the arrow towards oxygen like that, and the same thing with this other hydrogen, the arrow towards oxygen. The arrowhead points to the partial negative, to the more electronegative atom. So oxygen is more electronegative than hydrogen in the periodic table. That's because oxygen is in group number 6, group 6A. Hydrogen is in group 1A. Remember, it increases from left to right. So 1A is somewhere here, 6A is more to the right. So because oxygen is further to the right, it becomes more electronegative, and therefore the arrowhead, the dipole, points to oxygen. What about the electron pairs? The electron pairs are actually stronger in electronegativity value than any atom. So because of that, we draw larger dipole for the electron pairs. So very large like that. So you will see that you have the two hydrogen dipoles adding up to give you something like that. So the dipole moment equals to that. But now for the electron pair, you have a really strong dipole like that. So that's the dipole moment for that. So when you add these two together, you end up with a very strong dipole moment. So mu equals to that, and we say therefore water is highly polar. So that's why water is polar, because it has a very large dipole moment. Thank you very much for listening. Please take time to comment and also to subscribe and like the videos.